So let's work through some examples in 4.3, and I want to start with number 1 from homework. So the one I have is the integral from -9 to 9 of x cubed dx. Now in section 1, we looked at this symbol, and this symbol meant an antiderivative of x cubed. And there's a reason that we're still using that symbol, but when we have numbers here, this is a definite integral, not an indefinite integral, so it's not simply just an antiderivative. But this was related to the sum of f of x of I times delta x from I equals 1 to n, and then letting the limit of the n go to infinity. Or some books or some notations or use let tilde go to 0, which tilde is essentially, it's actually delta. Delta is just the width of each interval. In the examples that we've done in the last section, each of our intervals were a set width, but our intervals could be different widths per interval. Some intervals could be wider or narrower than others inside our interval. So for example, if we go from -9 to 9, each subinterval could be 1 unit wide, or some could be more than 1, some could be less than 1. But when we let n go to infinity, the number of subintervals, the number of rectangles go to infinity, each of them are going to get infinitely narrow, so we're letting the width, the change in our delta x, approach 0 for our sum. So for right now, we're going to evaluate this using our summation and letting our width go to 0 or n go to infinity. So we need several things. We need our delta x, which is b, the right side, minus a, the left side, over n. We're letting n be varying, so we're just putting n in there. So 18 over n is delta x. It turns out if we're going n going to infinity or delta going to 0, it doesn't matter if we do a left or a right-hand sum. So let's let our x of I be a plus I delta x, the right-hand sum. So -9 plus I times 18 over n. So that's going to be our x of I. So we need to substitute n to our function, -9 plus, we can call that 18i over n, times delta x, which is 18 over n. We need to evaluate that sum, and then we need to take the limit of it. So in order to evaluate that function at our x of I, we're going to plug that in for x, and we're going to cube it, which that's going to be a little bit aggravating. So I'm going to take a moment and go to another page, and let's take -9 plus 18i over n. If we square it, remember the shortcut to squaring it is to square the first one, so -9 times -9. Multiply those two together and double it. So if we multiply -9 times 18, we would get -162 and then double it. So that's going to be the coefficient of I over n. So -324 I over n. And then we square the second term. So 18 squared, 324, I squared over n squared. So that's from squaring it. We want it cubed, so we need to take that and multiply it again times -9 plus 18i over n. So now we just need to distribute 81 times -9, so -729. 81 times 18i over n, so 81 times 18 1,458, and that's I over n. Then negative 324, I over n times negative 9. So negative times negative will be positive. 324 times 9, 2,916. And that'll be I over n. That one times that one, a negative times a positive is a negative. 324 times 18. That'll be 5832. This one times that one will be I squared over n squared. And then we're going to distribute that one. So 324 times minus 9, we've already done 324 times 9, and that was 2916. So when we do that, that's going to be a minus 2916 I squared over n squared. And when we do this one times that one, positive and positive, that's going to be positive I cubed over n cubed, and whatever 324 times 18 is. 5832. So we need to combine like terms. We have a minus 729. This one and this one are I over n. So 1458 plus 2916. 4374. So that's I over n. Then we have some I squareds over n squareds. So 5832. Those signs are the same, so we're adding them. Type this in correctly. 8748. That's I squareds over n squareds. And then 5832. That's I cubes over n cubes. So that's what we get when we cube this. So let's group that together, and then let's copy that and move it back over here. So that's our f of x sub I. That needs to be multiplied times 18 over n, and then we need to sum that. So before we do the sum, we need to distribute. So distribute there, 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 and there. And when we distribute that, let's see what we get. We have a negative 729 times 18. So negative 13,122 over n. Then when we distribute that, we're going to have an I over n squared, and that's going to be how many? 4374 times 18, 78,732. And then when we distribute there, that's going to be an I squared over an n cubed. 8748 times 18, 157, 464. And then when we distribute there, that's going to be an I cubed over n to the fourth, and that's going to be 104,976. And no, I didn't do that off the top of my head. I looked somewhere and saw that. So that's what we're summing. And we're summing it from 1 to n. So we have 1, 2, 3, 4 terms that we're summing. So when we sum the first term, notice there's no I. So the first term, we're essentially summing a constant. And remember, when we sum a constant, we take the number on top times that constant. So our ends are going to cancel. And we're just going to be left with that negative 13,122. So we'll come back and do that in a minute. And then we're going to add the sum of the next term, 78732i over n squared. We're going to subtract the sum of the next one. And we're going to add the sum of the next one. Now, all of these terms that have i's in them, remember, I is the variable of our summation. And anything that is not our variable, anything that is a coefficient, we can pull in front of the sum. So for this one on the end, we can pull the 104,976 in front of the n, or over n to the fourth in front of the sum of the I cube. For this next one, we can pull the 157,464 over n cubed in front of the sum of the I squared. For the next one, we can pull the 78732 over n squared in front of the sum of the I. And when we summed the first one, we said that if there's not an I in there, that's a constant, and we take it times what's on top. Well, when we multiply that times n, those cancel, leaving us negative 13,122. So now we just need to take a moment and then do those sums. So you can see this gets to be quite tedious as we go through here. So let's add a page, and remember that the sum of I from 1 to n is n times n plus 1 over 2. We're going to benefit by having that multiplied out since we don't have a specific number for n. If we have a number for n, we plug it in, but since we don't, let's just distribute that and call that n squared plus n over 2. The summation of I squared is n times n plus 1 times 2n plus 1 over 6. That's supposed to be a 2. So if we distribute that, we're going to have an n times 2n, so that's a 2n squared. We're going to have an n and then 2 more n's, so a 3n and a 1. That's what we get when we distribute those two. If we multiply that times n, we get a 2n cubed, a 3n squared, an n, and then all of that's over 6. And then when we do our I cubed, that's n times n plus 1 over 2, all of that squared, or you could say that one squared, and that one squared. So we have 4 on bottom, we have n squared times n squared plus 2n plus 1, using the shortcut to square that out. If we distribute the n squared, that's n to the fourth plus 2n cubed plus n squared over 4. So since we don't know what the value of n is going to be, it's best, instead of leaving each of these in the first form, to go ahead and distribute those out. Now let's come back here, bring down the constant. For the next term, we're going to replace I with n squared plus n over 2. For the next term, our coefficient down, and we're going to replace I squared with, what was that, 2n cubed plus 3n squared plus n over 6. Let me double check that. 231 over 6. 231 over 6, that's right. And then for the last one, I cubed. What was I cubed? It was our exponents were 4, 3, 2, and 1, 2, 1. So 1 into the fourth, 3n cubed over 4. Is that what it was? One, 2, 1. I don't know where I came up with 1. That's supposed to be a 2. And that's supposed to be a 1. Okay. Okay, so we're getting closer. We just have some simplifying to do. So we have our negative 13, 1, 22. We can reduce that 2 goes into that 39,366 times. We can divide each of those by n squared, or we could say take this times that. And when we do this fraction times that n squared and that one cancel out, leaving us 39,366. When we do that times this one, this n and one of those n's will cancel out. So that's going to give us an n on bottom, 39,366 on top. Let's see, this 6 will go into that 26,244 times. So we can, if we distribute that times this, that n cubed and that n cubed will cancel out, leaving us that times 2. So I'm just going to write that for now. And then when we do this times that n squared will cancel 2 of those out, and that's going to leave us, let's call that 3 times 26,244. If that n squared cancels, that leaves us an n on bottom. When we do that n will cancel one of those n's, and these are supposed to be minuses because it's a negative times that. That's a minus. That's a minus. So this n will cancel one of those n's. So we're going to be an n squared on bottom, 26,244 on top. And then lastly, we're going to distribute here. And you might say, why am I not getting more particular numbers? We're going to see in a minute why we're not getting more particular numbers, why we're leaving this. So when we distribute here, let's see, we can go ahead and reduce this 4. Let's see. 4 goes into that 26,244. So when we distribute this times that, the end of the fourths cancel, and that leaves us 26,244. When we distribute it times that n cubed will cancel most of those n's out. So we're going to be left with some number over n, and I'm not really even at this point going to worry about what that number is. When we multiply here, that n squared is going to cancel one of or two of those n's out, leaving us an n squared on bottom, and we're going to have 26,244 on top. Now you might say, why am I not concerned about that number? This is why. This will give us, if we had that number there, and you told me what n is, this will give us the sum using fixed number of rectangles for however many rectangles you want. But we're wanting to take the limit as n goes to infinity. If we let n go to infinity, this is going to go to the exact area. So every one of these terms that have an n on bottom and a constant on top, that goes to 0 if the bottom goes to infinity. That goes to 0, that goes to 0, that goes to 0, that goes to 0. So our limit is left with negative 13, 122. plus 39,366, whatever we get there, so 26244 times 2, and that's a minus, so minus 52,488 plus 26,244. So if we combine these, let's see what we get. Negative 13,122 plus 39,366 minus 52,488 plus 26,244, and we get 0. Wait a minute, do what? We did all of that when we got 0. Well, actually, that is the correct answer. If we look at our graph looks like this. Y equals x cubed, and we're going from negative 9 to positive 9. That sum that we do is known as the Riemann sum. And while the Riemann sum we originally set up as being the area, that sum is not always the area between the curve and the x-axis. This is only the area if f is greater than or equal to 0 throughout the entire interval. If we take our function times delta x on this side, our function is positive, our delta x is positive, so we get a positive area for everything on this side. But if we do our function times delta x on this side, our function is negative. A negative times a positive delta x will give us a negative area. So all of these rectangles on this side are negative areas. Well, this is symmetric, so we have the same amount of positive area as we have negative areas. So when we add those together, they cancel out, and they give us a sum of 0. That doesn't mean that the area between the curve and the x-axis is 0. That just means when we evaluate that Riemann sum, we get 0. Now that is long and lengthy, and fortunately we're not going to have to do it this way for very long. But we will have probably at least one problem on the test where we have to evaluate some area using a Riemann sum. But fortunately the area that you give probably will not have any function values that are negative inside the interval. So that's one type of problem that we do in this section. Let's look at another type of problem. So now that we've gone through that long problem, let's do one that maybe will help your feelings a little bit. Number 2 asks us to rewrite this particular limit that is in the Riemann sum formation. Copy it correctly. So they go ahead and they substitute some things into a function. And they tell us our interval, and they want us to translate this into a definite integral. And they give us this part, and they want us to fill in this box, and then we're told dx. So when we go between the two notations, this is the function, delta x becomes dx. So in this notation, c sub I is essentially where our x sub I was. We're just using a different notation, but x sub I, c sub I are essentially the same. So this is where our function goes. So our function is 6 over x to the 8th. We're plugging a c sub I in place of x. So x to the 8th is our function on bottom. Our interval goes from 3 to 9. So at the bottom we have a 3, at the top we have a 9. And that's all we have to do. So these two statements are equivalent to each other. On number 4, they give us a picture. and we go from 0 to 2 in the x direction, we go up to 6 in the y direction, and our function is 6 minus 3x. And they ask for a definite integral that yields this area. So instead of writing a Riemann sum that yields that area, write a corresponding definite integral. So our region has an interval that starts at 0 and goes to 2. Our function that is above the x-axis is the function 6 minus 3x. So that's our f of x. And then our delta x, we actually put a dx for it. So that's all they're looking for there. So let's see if there are any other specific ones. There's one or two problems where they give us a function and they want us to sketch it and then just use geometry to find the area. It's probably going to be something like a rectangle or a triangle. Then they give us some problems like this. And they tell us this area or the value of that sum. It may or may not be an area. Then they give us the value of this sum. And then they give us the value of this, or we could think of that as 1 dx. And then they ask us some questions. So one question says, if we change the limits and go from 2 to 2, what will the value of that sum be? So if we look at our graph is y, our function is y equals x, which is a straight line. If our interval starts at 2 and ends at 2, that means our interval has no width. Well, how can you get an area that has no width? It has length, but no width. So if we calculate the area of that rectangle, if we multiply its length times no width, then we have no area. That's just the area that starts here and ends here, no width, hence an area of 0. Alright, so let's do another one. Let's do, what if we want the area from 2 to 8 of 2x squared minus 3x plus 5? Well, we were given the area of x cubed of x and dx, so I thought we had an x squared, so we don't. So let's change that to an x cubed. So our properties of sums apply to our definite integrals because it's essentially the same thing. So when we have a sum with multiple terms, we can break it into separate sums. So if we have a definite integral with separate terms, we can break it up into separate definite integrals, and we can put our coefficients in the front. Same thing on the next one. Put the coefficient in the front, and each of these definite integrals go from 2 to 8. Put the 5 in the front. And also each of these have a function and dx. So we need a dx here, and a dx here, and a dx here. In our problem, we were told the value of each of these definite integrals. We were told that value, and that one, and that one. So we're going to have twice that first one. We were told that this sum is 1020 minus 3 times the next sum. We were told that sum is 30 plus 5 times this last sum, and we're told that one is 6. So our answer is 2040 minus 90 plus 30. 2040 minus 90 plus 30, 1980. So that's what we get for that one. Now let's do one more of these. let's look at the sum from 8 to 2 of x dx. We know the sum from 2 to 8 of x dx is 30. So if we go in the opposite direction, if we go from right to left instead of left to right, then for that one, we just take the opposite of it. And they show us that property. Honestly, that's not one we use very often. That comes from the difference in the delta x's. The functions are the same. For the bottom one, delta x is 8 minus 2 over n. For the top one, delta x is 2 minus 8 over n. So our delta x's have opposite signs. Our functions are the same and our intervals are the same, but if our delta x changes signs, that's going to change the result of our sum. But just to let you know about that property. So that should put you in pretty good shape to finish out the homework for this section. So I just wanted to work through a couple of those examples, particularly the first one, because the first one was a little bit of a booger. But the rest of them hopefully are not so bad.